Okay, let's get into this paper. Flowmap distillation without data. We're really talking about the biggest headache in high-fidelity generative models, which is just how slow they are.
Exactly. Latency, you've got these incredible diffusion and flow models that produce just stunning images.
Right.
But they're so slow, they have to solve an ordinary differential equation step by tiny step. That's the NFE bottleneck everyone talks about.
And the common fix for that is distillation. You take a huge, slow teacher model and you compress it into a super fast student, a flow map. But that old method has this fatal flaw they call teacher-data mismatch.
Yeah, that mismatch is the core problem. It happens because the student is trained on a static data set, but that data set just doesn't represent the teacher's actual creative process, especially when the teacher is using tricks like classifier-free guidance.
Which brings us to the solution in this paper, FreeFlow. It's a completely data-free framework. It just throws out the data set.
It's such a brilliant move. It sidesteps the whole mismatch problem by sampling only from the prior distribution.
The random noise at the very beginning.
Exactly. It's the one and only point where the student and teacher are guaranteed to be perfectly aligned. From there, it uses this really clever predictor-corrector approach.
So it has two jobs. Predict the path forward, that's the generating velocity, or V dollars, and then correct its overall position, that's the noising velocity, V dollars.
And the results really speak for themselves. They distilled from this monster model, SciTXL2 plus REPA, and FreeFlow hit an FID of 1.45 on ImageNet 256 by 256.
With just one sampling step.
One step. That's not just a small improvement. It's, it feels like a whole new way of thinking about accelerating these models.
So to really appreciate this, we have to set the stage with that latency bottleneck. When you generate an image with one of these models, you're literally solving an ODE backwards in time.
And solving an ODE numerically means taking lots and lots of small steps. If you want a really high-quality image, you're looking at hundreds of function evaluations, hundreds of NFEs.
For one single image.
For one image, which is why you don't see these models in, real-time applications everywhere. The compute cost is just massive.
So the big idea that gained traction is to use flow maps, what they call Phi-theta, instead of all those tiny steps.
The Flowmap just learns the whole solution at once. It's trained to approximate the entire generative path. So it can make these huge jumps from noise to image, bypassing all that iterative work.
And distillation is really the smartest way to build one of these. You don't start from scratch.
No way. You take a state-of-the-art teacher model, maybe a giant diffusion transformer that's already been perfected with advanced techniques like RBT.
Right, something that already has all that baked-in knowledge.
Exactly. And you distill that knowledge into the fast student. It's incredibly modular. The teacher might have cost millions in compute to train, but you can compress its peak performance without having to replicate that whole process.
So just to ground ourselves in the math for a second, it all comes down to a vector field, two others. Sampling is just integrating along that field backward in time from your starting point.
Which is just random noise. The prior distribution, t-ply at time equals 1.
All the way down to the final image, the data, at time t equals 0.
Okay, so now let's get to the heart of the issue. The whole reason FreeFlow was invented, this teacher-data mismatch.
Right, so the conventional way of doing distillation, you'd grab a big data set.
Yeah, a static external data set. You take images from it, you add some noise to them to create these intermediate states.
And then you tell the student, hey, at this noisy state, try to act just like the teacher.
Exactly. The student is learning to follow a path that's anchored to that external data set.
But here's the kicker and the core insight of the paper. That path, the one from the data set, might be completely different from the path the powerful teacher model actually takes to create its best images.
And you have to ask, why would they be different?
Yeah, why?
Well, the biggest reason is classifier-free guidance, CFG. It's used almost everywhere now.
It's what makes the images so sharp and on prompt.
It gives the model a huge quality boost. But by doing that, it pushes the final generated images away from the distribution of the original training data. So if the endpoint is different,
then the whole path to get there must be different too. The teacher is taking its own road, not the one laid out by the old data set.
That's one big reason. Another is fine-tuning. Say the teacher was trained on dataset A, then fine-tuned on dataset B. Its internal vector field has been deliberately changed.
So if you use dataset A for distillation, you're already out of sync.
You're totally out of sync. And then there's the worst case, which is actually super common. The teacher was trained on proprietary data you can't even get.
Ah, so you're forced to use some other proxy dataset.
which guarantees a mismatch from the get-go.
But couldn't you just use a gigantic proxy data set? Wouldn't that, average out the error?
It's not about size, it's about alignment. And they actually tested this. They took a great teacher model and just started adding more and more data augmentations to the distillation data set.
So they were deliberately making it misaligned.
Deliberately. And the student's performance just tanked. It proves how sensitive the student is to the fidelity of that proxy data. The teacher's quality can't save it if the map is wrong.
So the teacher's true path and the proxy data path are diverging all over the place.
Everywhere from T0 to almost T1. But, and this is the beautiful part, at the very beginning, at T1, they have to be identical.
The prior distribution, the random noise.
That is the single point of guaranteed alignment, the shared origin.
And that's the entire philosophical foundation for FreeFlow. Forget the risky data. Let's just start from the one thing we know is true, the noise.
Okay, so diving into the mechanism, they have this really elegant two-part system, prediction and correction.
So FreeFlow samples a $0.0 in the noise distribution, B-tax. And that's it. From there, it has to figure everything out on its own.
The first part is prediction, using what they call generating flows, VD dollars.
Okay, let's try an analogy. Imagine the teacher is driving on a perfect road, but the road is invisible. The student starts at the beginning, at the noise point, and has to predict where that invisible road goes.
That's a great way to think about it. The student is trying to match its own instantaneous generating velocity, its V dollars, with the teacher's velocity, U.
And it does this by checking how its own predictions change as it tries to take bigger and bigger steps.
Right. It's a self-referential process. The student is essentially learning to ride the teacher's vector field based purely on its own evolving predictions. It all starts from that one anchor point in the prior.
That sounds incredibly efficient, but the paper points out a huge potential problem.
Compounding errors.
Exactly. The student is just an approximation. It's a tiny mistake in its first prediction.
Gets amplified. If it predicts a slight left turn when the real road goes straight, every subsequent prediction is now starting from the wrong place. The error just grows and grows.
You can see it so clearly in Figure 4 of the paper. The student's path just veers off dramatically from the teacher's true path as it tries to predict further ahead.
And that is precisely why you need the second component. Correction with noising flows, value dollars.
So if prediction is about finding the local direction building the road step by step, correction is about the global picture.
Yeah, it's about checking the overall map. This part is inspired by density matching ideas like variational score distillation. The goal is to make sure the overall distribution of the students' generated samples matches the teacher's.
So it aligns the student's noising velocity, which is sort of the force needed to keep the distribution in the right shape, with the teacher's underlying velocity dollars.
And the genius part is, this correction objective also samples only from the prior noise. So you have these two signals both starting from the same safe place.
One signal, VG is telling the student, go this way right now.
And the other signal, VG is saying, and by the way, make sure the cloud of points you're generating looks correct overall.
So the final framework combines both. Prediction builds the path, and correction keeps it from flying off the rails. They use an adaptive balancing strategy to mix the gradients.
And they found something really interesting there. The best results came when they actually applied a stronger decay to the prediction loss signal, the VG one.
Wait, that seems counterintuitive. If prediction is what builds the path, why would you dampen its signal?
Well, the hypothesis is pretty cool. It's to stop the two signals from fighting. Sometimes the best instantaneous direction, the V signal, might conflict with what's best for the overall density shape, the V signal.
Ah, I see.
So by dampening the local short-term signal, they let the more foundational global correction signal win out, leading to a much smoother and more stable training process.
And when we get to the experiments, you can see this combination just works. The results are, well, they're state-of-the-art.
All right.
Especially for one NFE sampling.
That one-step generation is the holy grail for latency. An FID of 1.45 on ImageNet 256 by 256 and 1.49 on 512 by 512, that's a huge leap forward. It soundly beats all the data-based baselines like FACM.
The synergy experiments really sell it too. They showed that if you train with prediction only, you hit a wall because of those compounding errors.
Right, it just plateaus. And if you train with correction only, you start to get mode collapse.
But together,
it's strictly better. They provide sustained, stable improvement. One builds the path, the other keeps it true.
What's also amazing is how fast it trains. They were already beating strong baselines after just 100,000 training iterations. It shows this data-free idea isn't just a theoretical curiosity, it's actually a super efficient way to train.
It really is. And think about the practical benefit for an engineer trying to deploy one of these. The student just inherits all the magic from the teacher.
You mean like the REPA fine-tuning?
Exactly. You don't have to figure out how to implement all those advanced training tricks for your student model. You just distill the final perfected teacher. It's a huge shortcut.
Okay, let's talk about the big practical payoff, because this is a game changer for actually using these models. Inference time scaling with a best-of-n search.
Right. So to get the absolute best image quality, people often do a best-of-n search. You generate, say, 20 different images from 20 different noise seeds.
And then you pick the best one.
But if your teacher model takes 100 steps per image, you've just spent 2,000 NFEs just to find one good starting noise.
Which is completely impractical for any real application.
Here's where FreeFlow shines. You now have a super fast one-step proxy for the teacher, so you can run that entire best-of-n search on the cheap student model.
Because it's learned the teacher's flow so well, it's a great filter for finding the best starting noise, the best Zollersteed.
Exactly. Once the fast student finds the single best noise seed, you take only that one seed.
And give it back to the slow, powerful teacher for one final high-quality generation.
This totally flips the script on inference costs. They showed that finding the best noise with the student and then generating once with the teacher took a total of only 80 NFEs.
And that actually beat the teacher's standard unoptimized sampling, which took 128 NFEs.
It's an incredible efficiency gain. You've made these giant, powerful models practical to use at scale just by adding a cheap distillation phase. It's a real engineering breakthrough.
So to wrap up our look at Flowmap distillation without data, this paper really makes a powerful case that this data-free approach isn't just a clever idea. It's fundamentally more robust than the old database methods.
It completely solves the teacher-data mismatch problem by going back to the one point of certainty, the prior distribution.
And the success really comes from that beautiful alignment of two different signals. The local prediction from the generating velocity, VAG dollars, working hand in hand with the global stabilization from the noising velocity, VOG dollars.
They managed to reconstruct this incredibly complex journey just by knowing the starting point and carefully balancing those two forces.
Which brings us to a really provocative final thought. If you can achieve state-of-the-art results for a complex task like this, purely by sampling from noise and learning from a strong teacher, does it challenge our reliance on massive data sets for knowledge transfer?
It really does. It suggests that for many distillation scenarios, you might not need an external dataset at all. If the teacher model is good enough, perhaps all the information needed to transfer its skill is contained within its own vector field, accessible from that universal starting point of randomness.
So the data is the teacher, not a separate data set.
Exactly. It's definitely something to think about the next time you're trying to compress a model and worrying about what data to use. Maybe the answer is none at all.